Equations of lines and planes, Level 3. In the previous video, we derived the vector equation, parametric equations, and symmetric equations of a line in space. In this video, we will go over 3 basic examples that make use of these 3 equations. Alright, let's jump straight into the first example. Determine whether each point lies on the line. In this problem, we are given parametric equations of a line in space, along with the coordinates of 2 points. We are asked to determine if these points lie on the line. Recall that a point will lie on a curve if the point's 3 coordinates satisfy the parametric equations for the same value of the parameter t. We can determine this in a couple of ways. We can substitute the coordinates of the point into the parametric equations and solve for the parameter t for all 3 parametric equations. If all 3 parametric equations yield the same value for the parameter, then the point lies on the line. On the other hand, if at least one equation has a distinct parameter, then we can conclude that the point does not lie on the line. So let's go ahead and substitute the coordinates of the first point into the parametric equations and solve for the parameter t. Doing that, we obtain the following. Notice that all 3 parametric equations yielded the same parameter t. This means that the first point lies on the line. If we had the symmetric equations of the line, we would solve it in a similar manner. In this case, we would substitute the point's coordinates and check to see if all 3 equations yield the same value. We can also show that a point lies on the line by determining the parameter t for one of the point's coordinates and use it to check if the parameter satisfies the 2 other parametric equations. Let's illustrate this with the second point. Let's first determine the parameter t for the first parametric equation. So we substitute the x-coordinates into the first parametric equation and solve for the parameter t. Now that we have this parameter, let's substitute it into the other 2 parametric equations and check to see if we obtain the same y and z coordinates of the point in question. Notice that the second parametric equation is not satisfied. And at this point, we can stop here, since we only need one parametric equation to be false to conclude that this point is not on the line. As a check, notice that the third parametric equation is also not satisfied. This means that the coordinates of this point occur at different values of the parameter t. Unlike the first point, where all coordinates exist at a common parameter t. So the first point lies on the line, and the second point does not. And this is our final answer. Let's take a look at the next example. Find a vector equation, parametric equation, and symmetric equation for line L that passes through point P and is parallel to vector v. In this problem, we are asked to find the equation of a line in space using all 3 forms. Let's first determine the vector equation of the line. Recall that the vector equation of a line is written by finding a position vector that terminates at a point on the line. In this case, the initial point, plus a parameter multiplied by a vector parallel to the line. Notice that we are provided with a point and it is known that line L passes through this point. We will use this point as the terminal point of a position vector r0. We are also given a vector parallel to the line. So we go ahead and substitute these vectors into the vector equation of a line in space. Now it is just a matter of multiplying the parameter t with the components of vector v. Then we go ahead and add the vectors on the right side of the equation, component-wise. Doing that, we obtain the following vector equation. Note that we can also rewrite this vector equation by using the standard unit vectors I, j, and k. Next, let's find the parametric equations for line L. To find a set of parametric equations, we will break apart the components of our vector equation into individual equations, one for the x component, y component, and z component. Notice that the parametric equation makes use of the coordinates of the point where the line passes through, and also uses the direction numbers of vector v. Also notice that the parametric equations are essentially the components of the vector equation of the line. Lastly, we can find the symmetric equations of the line by solving for the parameter t for each parametric equation and equating all three expressions to one another. Doing that, we obtain the following symmetric equations. Notice that the symmetric equations also use the coordinates of the point where the line passes through, as well as the direction numbers of vector v. It is important to note that the vector, parametric, and symmetric equations can be obtained by simply rewriting one form into any of the two other forms. Once you know one form, the other two are also known. It is just a matter of rewriting them. Alright, let's take a look at the final example. Find a vector equation, parametric equations, and symmetric equations for line L that passes through point A and point B. At what point does this line intersect the xy plane? In this problem, we are asked to find a vector, parametric, and symmetric equations of a line that passes through points A and B. We are also asked to determine the point in which this line intersects the xy plane. Let's first determine the equations of the line. Notice that we are given 2 points, A and B, but we are not provided with a vector that is parallel to the line. We're going to have to generate a parallel vector by using these 2 points. This is very similar to the way we found the slope of a line in r², when we were given 2 points. Recall that we had to find the change in y and the change in x. For this problem, we can find a vector v that is parallel to the line by finding a displacement vector. We will use point A and point B to find this parallel vector. So we use point B as the terminal point, and use point A as the initial point of the displacement vector v. We then subtract the coordinates of point A from the coordinates of point B as follows. Doing that, we obtain the following. This is one of many possible vectors that are parallel to the line. We just happen to use this particular vector because we can determine it quickly with the given points. There is nothing stopping you from using a scalar multiple of this vector instead of the one we found. And in fact, you might want to make the components of direction vectors nicer to work with, and this can be done by scaling them. Alright, now that we have a vector parallel to the line, we can now write the vector equation of the line. We need to choose an initial point for our vector equation. Since it really does not matter which point we choose, we're going to choose point A for our vector equation. You're free to use point B as well. Substituting the components of the displacement vector's terminal point A and the components of the parallel vector v, we obtain the following. Now it is just a matter of distributing the parameter t and adding the resulting vectors. Doing that, we have the following vector equation of the line. We can also rewrite this vector equation by using unit vectors. Next, let's find the parametric equations of the line. We can obtain the parametric equations by isolating each of the components of this vector equation, yielding 3 separate equations, one for each component, as follows. Lastly, we can generate the symmetric equations by solving for the parameter t for each parametric equation and equating all 3 expressions to one another. Doing that, we obtain the following. Next, let's figure out the coordinates where this line intersects the xy plane. We can determine the point of intersection by remembering that any point located on the xy plane will have a z-coordinate equal to 0. So we can approach this in 2 ways. We can use the parametric equations and set z equal to 0 on the third equation and solve for the parameter t. This will provide us with the value of t where the z-coordinate of the line is equal to 0. We then use this value and substitute it into the other 2 parametric equations and solve for the x and y coordinates. We can also use the symmetric equations and set the variable z equal to 0. This would generate 2 separate equations that can be used to solve for the x coordinates and y coordinates of the point. Using this method, we obtain the following 2 equations. Remember that we can cross-multiply proportions to rewrite them into an equivalent equation. Solving for x and y, we obtain the following. In the end, line L intersects the xy plane at the following point. And this is our final answer. Alright, in our next video, we will take a look at slightly more challenging examples involving the equations of lines in space.